Right, so we will pick up from where we left off yesterday. We did a fair bit yesterday during our last session. In particular, we talked about this remarkable thing called the induction equation, which you will see very often in MHD. If you remember, this form of the induction equation is valid only for infinite conductivity, right? If you have finite conductivity, you will have an additional term which is proportional to del square B, right? You'll have an additional term here, and the proportionality constant contains the conductivity, right? So this term, the diffusive term, assumes importance only when the conductivity is finite and not infinite. Okay, and we also talked a little bit about the magnetic Reynolds number R sub m. Okay, and the magnetic Reynolds number is essentially the ratio of it looks very much like the fluid's Reynolds number, except here you have the appearance of the resistivity. Okay, it is something like the resistivity appears at the bottom. So for an infinitely conducting plasma, the Reynolds number, the magnetic Reynolds number is formally infinite. Okay, so whereas for plasmas with a large conductivity, with a small conductivity, rather large resistivity, the magnetic Reynolds number is small, and in astrophysical situations typically the Reynolds number is very high. Okay, so we discussed all that. That was a very quick recap. Now what we will do, and we stopped last time, was in starting to discuss some curious aspects about current density J in magnetohydrodynamics, in ideal magnetohydrodynamics, for which the conductivity is assumed to be infinite. In ideal MHD, the conductivity is infinite, so that the induction equation is just this with no additional terms. Okay, so now you recall how we derive this. E equals, so this is the electric field in the lab observer's frame, right? In the fluid frame there is no electric field. If the plasma is infinitely conducting, the fluid frame, by definition there cannot be any electric field. However, in the lab observer's frame, and it's only in the lab observer's frame that this makes sense, because you have the appearance of a V. It's only for the lab observer you have a finite velocity for the plasma, right? When you're sitting inside the plasma, there's no V, right? So it should be obvious to you that this refers only to the lab observer. So in the lab observer's frame, there is a finite electric field. It's another matter that since the V is non-relativistic, in other words V over C is very, very small, the magnitude of the E will also be small, but nonetheless it's small but finite. Okay, so now what we do is we substitute this in Ampere's law to get this kind of an equation. Okay, and for non-relativistic speeds, when V over C is much less than 1, this term is negligible, right? So we don't consider this term, and so you simply have J equals C times curl of B, right? And if you draw an analogy with the electrodynamics that you already know, you will immediately recognize that this is just the displacement current term. Okay, the regular current is not there at all. Okay, the non-displacement current part of it is not there at all. Now what about it? You take the divergence of both sides. Yeah, since the divergence of a curl is always 0, right? So this is always 0. It follows that the divergence of the current is equal to 0. So the currents have no sources or sinks. This is something that we need to keep in mind very clearly, because this is one of the curious aspects of magnetohydrodynamics. We will see why, right? So the divergence of J is equal to 0. So the currents two have no sources or sinks. And the other thing is the charge continuity equation, which essentially said that divergence of J plus d sigma dt was equal to 0. It's since the divergence of J is equal to 0, d sigma dt is also equal to 0, right? So in other words, if the plasma is charge neutral to begin with, sigma is the net charge density, you remember, right? So if the plasma is charge neutral to begin with, it remains that way for all time. Okay, and you remember we talked about one of the basic assumptions of MHD, and that has to do with the fact that the plasma, although it's comprised of charged particles, on large scales it's charge neutral, and it is only on these large scales that our theory is valid. So we are really talking about a bit of a curious beast here, a charged but nonetheless charge neutral fluid which comprises of charged particles, but nonetheless on the whole is charge neutral, and it carries a current density. Very, very strange, but these are things that you'll need to get used to. And what is this? The fact that divergence of J is equal to 0, what's that telling you? Is telling you that if the plasma is charge neutral from the at an early time, it remains that way. MHD ensures that it will never acquire any charge. Okay, it is somewhat like this. Divergence of B equals 0 is not guaranteed in MHD. Okay, what's guaranteed is simply that the time derivative of the divergence of B is 0. So if you ensure the divergence of B equals 0 at the very beginning, then it remains that way, somewhat like that. Okay. So now let's talk a little bit more about currents, because currents are in particular current density. Actually, I should say current density, because it's a bit of a strange thing. Our usual ideas about currents from electrical circuits don't quite apply here. So let's spend a little bit of time trying to understand what the status of currents in MHD. Okay, in MHD, V and B are the primary variables. Okay, the current is somewhat of a secondary quantity. Okay, computed via Ampere's law. So in other words, I would go so far as to say that J is merely a proxy for curl B. It has, I would even go so far as to say that it has no particular physical significance. Physical significance. Okay. I insist on this. We will see why. Okay. So therefore, I would, whenever someone asks you what is the actual meaning of current density, you just point them to this equation. This, of course, in CGS. Okay, in CGS, you have the appearance of the C over 4 pi. In SI or MKS, this constant will be slightly different, but nonetheless, it's essentially curl of B. So if someone asks you what is the current density, what is the meaning of the current density in MHD, you say that it's essentially, don't worry about it, it's essentially telling you something about the curl of B. That is it. Okay. Why? Because we will see this. Why do I say that it has no real physical significance? First of all, we established in the last slide that currents in MHD have no sources or sinks, right? Because this is because the divergence of J is equal to 0, right? As we showed in the last slide, the divergence of J is equal to 0, and so that means that there are no sources or sinks for current density in MHD, right? So this is a strange thing, and in other words, there are no batteries. Okay, a battery is a source and a sink of current, isn't it? The positive terminal of the battery is a source of current, and the negative terminal of the battery is a sink of current. There are no sources or sinks in MHD. There are no batteries. Very important. Normally our notion of current in flowing in wires is precisely this. You always think of a battery or a generator which generates the current and the other side taking the current back, but there are no such things in MHD. Also, it is not as if currents are carried by the fluid, as in it's tied to the fluid. I mean, this is the reason I'm emphasizing this so much, is because these are common misconceptions. You have a charged fluid, you have a fluid comprising charges, and it's flowing, and it's natural to think that the flow of these charges comprises the current. That is not so. Okay, it is not as if it's not as if the flowing charged, well, first of all, the fluid is not charged, as we said. Over large length scales, the fluid is electrically neutral. But since the fluid comprises of charged particles, many people think of it like this: fluid carries a current. It is not so. This statement is not correct. Okay. Or as in, it's not as if the currents are tied to the fluid. There is really no current conservation to go with fluid displacement. This is also very, very important. There is charge conservation, but there is no current conservation. Okay, very important. In fact, since currents are simply the curl of B, you see here, apart from a constant, they are just the curl of B. It follows that the only currents there are cross field. Okay, because by definition the curl of B is perpendicular to B. So, the direction of the current density is actually perpendicular to B. The cross field meaning cross, they are perpendicular to the magnetic field B. Okay. This is also something that bears looking at, and you should let this sink in a little bit. So, one has to really envisage very vanishingly small non-ideal, if you insist on a physical picture for the current, which I really would not pay much attention to. I would simply say the current really has no explicit physical manifestation in magnetohydrodynamics. One has to stop thinking in terms of currents being carried by wires with a source and a sink. That is not how it is in magnetohydrodynamics. The meaning of the current is just the current is simply a proxy for the curl of B. But if you insist on a physical picture for the origin of current, you have to envisage vanishingly small non-ideal effects. We are talking about ideal MHD, but still, if you insist on a physical picture, then you have to envisage non-ideal effects, which are of course vanishingly small, because we are talking about ideal MHD. For instance, what are the non-ideal effects we are talking about? Finite resistivity or collisions. Remember, in MHD the resistivity is technically 0. Okay, so we have to envisage finite resistivity or collisions in order to justify these kinds of cross field currents. Okay, it's somewhat like this. Yeah, so what this means is that think of a magnetic field, right? And think of the orbits of protons and charged particles. Remember, there are no charged particles in MHD, there are no particles in MHD, but still, since we are trying to ascribe a physical meaning to the current, let's for a moment think about protons and electrons, yeah, gyrating in opposite directions, right? They obviously, they'll both gyrate around the magnetic field, but in opposite directions, right? Okay, and now what's happening is there are little collisions with each other, which make these gyro motions slightly displaced. Okay, so what happens is the proton motion does not exactly cancel out the electron motion. So therefore, there is a slight charge displacement, and that gives rise to a small current. Okay, and since the gyration is perpendicular to the magnetic field, this current that we are talking about, this small current which arises due to finite resistivity or collisions, really, which arises due to collisions, which in turn give rise to resistivity. Yeah, which I mean, so this small charge imbalances which arise due to collisions, they give rise to slight charge separations in a plane that's perpendicular to the magnetic field, and that results in these cross field currents. But really this is a lot hand waving, frankly, and I personally would, I mean, some people like to resort to physical pictures, which is why I told you this, but I personally would not pay too much attention to these things. I would simply say that the current density is this J is really no point in trying to ascribe too physical a meaning to the current density. I simply say that the current density is just this equation, so it's simply a proxy for curl of B. That is it, and there's no need to discuss anymore. Okay, all right. So these are some of the strange things about current density of currents in MHD. So it's worth, I thought it was worth spending some time talking about it. Okay, so let's now get on to the momentum equation, the equation of motion. As we know, this is the momentum equation. We have spent a fair amount of time talking about the momentum equation in fluid dynamics. You remember the Euler equation and the Navier-Stokes equation, all of them are the momentum equation. Now, how is it altered? That's the whole point. Why are we talking about MHD? Because in a magnetized fluid, the fact that there is a magnetic field in the fluid means that there will be additional terms to the equation of motion. And what is that? You already have a fair idea of what it would be. It has to be something like the Lorentz force, and that's exactly what it is. We'll see what. So the fluid carries a current J. Mind you, what it simply means is that the fluid has a curl of B. Okay, because the current J is simply the curl of B. Okay, so and the Lorentz force per unit volume on this fluid is simply J cross B. Okay, so this is the force density. Force density. In other words, force per centimeter cubed, and those are the dimensions of this. And so that's simply J cross B. This simply arises from QV cross B, the kind of thing that you're already familiar with. Yeah, and so QV would be J. Yeah, but since there are no discrete charges in MHD, I would not like to appeal to discrete charges. It's simply J cross B, right? And we know that J is just curl of B, yeah, and so that's what it is. So this is the Lorentz force per unit volume on this fluid. So this is the force that needs to be added to the momentum equation, to the F equals ma. We already know the way to write down ma. We already know the way to write down different kinds of F, right? The pressure gradient, the body force and all that. And this is the new piece. This is the new term that needs to be added. Okay. Now here are a few curious things. Again, curious things. MHD is all about, I mean, the point is, many of our intuitive ideas don't quite hold in MHD, and so it's important to pause and look at these things. There are a few curious things about this force. Unlike our usual notion of a Lorentz force, which is a force on a charge, right? Q V cross B. This is how we normally think of as Lorentz force, right? It is a force on a charge Q. However, what is this? This fellow is really, this is the force on an element of electrically neutral. There are no charges. The element of fluid is actually electrically neutral, but it still carries currents. Very important. So the curious thing about this Lorentz force is that unlike our usual notion of Lorentz force, which is force on a charge, we normally write the Lorentz force as F equals Q V cross B. This is not how we should think of the Lorentz force in MHD. Why? Because there are no charges at all. This is actually the force on an element of electrically neutral. There are no charges. but the fluid is electrically neutral, but nonetheless it still carries current. Okay. So, these are a couple of curious things about this Lorentz force, and so this is important to keep in mind. The other thing is that the Lorentz force is quadratic in B. It goes as B squared, you see, B here and B here. So, it goes as B squared. In other words, so what is the implication of that? What about it? It does not care about the direction of B, whether B is this way or this way. It does not matter, the Lorentz force will still be in the same direction. This is another strange thing. Okay. So, important to keep these things in mind, and it is true that this is the only additional term that appears in the momentum equation. So, it is almost as if we can take this term and dump it into the momentum equation that we are already so familiar with, and we can go ahead, yes, but it is important to understand the features of this term, okay, and that is what we are doing now. Yeah, and in fact this is true for the induction equation as well. The induction equation that we wrote, that was also quadratic in B. Okay. All right. And of course, as we know, apart from Lorentz forces, there can also be other forces such as the gravitational force, the body force, right, and so we know this anyway from regular fluid dynamics. There is no need to go too much into it. Only real additional term is this, and it is important to keep these two curious points in mind about the Lorentz force. Okay. The other, as far as other conservation equations, right, there is a mass conservation equation, of course, which we are very familiar with. So, we will go straight ahead. So, that is the Eulerian form, and this is the Lagrangian form of the mass conservation equation. We have seen this. So, we will go right ahead past this. And depending upon the situation, one has a thermodynamic closure equation, something like P equals P, which is a function of rho and T, or maybe a polytropic equation like P equals K rho raised to gamma. So, you might have this, or sometimes an explicit, instead of this, you might have an explicit energy equation. All right. So, that depends on the situation. Usually, however, there are only two coupled equations for the two primary vector fields V and B that are usually solved. Okay. Remember this with regard to MHD. We might talk a lot about current density and so on and so forth, but it is only a derived quantity. Okay. J is only a derived quantity. The primary quantities are just the fluid velocity and the magnetic field, that is it. Okay. And these are the coupled equations that you solve the induction equation and the equation of motion or the momentum equation. These are the only two equations that typically need to be solved. Of course, you would have an energy equation sometimes in the guise of a thermodynamic closure equation or an explicit energy equation. Okay. So, and you remember how the equation of motion looks like. We are already familiar with this piece, with this piece, and with this piece. This is the only new piece here, the Lorentz force, right? And so that is that. So, the induction equation and the equation of motion, these are the only two equations that normally need to be solved in magnetohydrodynamics, and of course, the mass conservation equation, which is this. Okay. The rest of the point I want to make is that although we are talking about a magnetized fluid, the rest of Maxwell's equations, which is where we got the induction equation from, might as well forget about them. They are not really needed. Once we have derived the induction equation, we can just keep it. I mean, we can just forget about the rest of the Maxwell's equations. Okay. We can rely, we are already familiar with the equation of motion from fluids. We are already familiar with the mass conservation equation. We already know this, and we are also in fact familiar with the energy equation either in this guy's or in that guy's. Okay. And so the only new equation that we need to be worried about is just the induction equation. The other bunch of Maxwell's equations, not important anymore, because we've already derived the induction equation from those, and that's it. We can forget about the rest of the Maxwell's equations. And of course, it's also, there is an important new term in the equation of motion, and that has to do with the Lorentz force. Of course, that's there. But it's curious that we don't have to worry about Maxwell's equations anymore. All right. So that's how it goes. And the next thing that we will worry about a little more is the nature of the magnetic fields now. Okay. What the magnetic fields do to the equation of motion, and like this line says, since magnetic fields are pretty much the only vector field that is quote unquote solved for in MHD, in that V, you see, the velocity field is typically given or typically prescribed. Okay. I give you a certain velocity field. I give you a fluid that's flowing in a certain manner, and MHD typically likes to answer, okay, given this velocity field, how does the magnetic field that's present in the fluid, how does it evolve? How does it evolve with time? Okay. So magnetic fields are pretty much the only vector field that is solved for in MHD. So it's important to try and understand its properties a little more. So you look at the equation of motion, where this contains only the pressure term, the gradient of pressure term, and the Lorentz force term. We've neglected body forces or gravity. Yeah. And the first term of the RHS, which is the essentially the gradient of a scalar pressure, it's just the gradient of a scalar pressure, and therefore it would make sense to expect that the second term, the Lorentz force, should also have a similar character. At the end of the day, this should also look like the gradient of a scalar pressure. This entire term, this curl B cross B. In fact, it does. It can be expressed as a divergence of a second order tensor, which is called the magnetic stress tensor. And yeah, so the magnetic stress tensor, which is M, this thing in red, okay, this thing can be expressed as a divergence of a magnetic stress tensor, and dimension wise, it's the same as gradient, so the gradient of a scalar pressure. That's what this is. Okay. And the elements of this tensor, the ijth element of this tensor is given by this 1 over b square, 1 over 8 pi b square delta ij. So these would be the diagonal terms, and these would be the off diagonal terms. So this is the diagonal term of the stress tensor, and these are the off diagonal terms. These Bi, Bj. Okay. So the stress tensor would essentially be a matrix like that, like that, like that, this, and the diagonal terms, this, and this, are given by 1 over 8 pi b square, and the off diagonal terms would be given by Bi, Bj, where suppose this is x, xx, xy, so the xy would be bx, by, and this would be xz, so that would be bx, bz, so on and so forth. Okay. So we will discuss, given this, there are some curious properties of this magnetic stress tensor that need to be understood before we go forward in MHD, and we will discuss it when we take it up next. So that's all for the time being. Thank you.